Hello everyone. I have a strong feeling I'm live right now, so please just confirm to me by chatting in the chat to let me know that you can hear me. Alright, I'm going to now transition to this, and so I hope you can see my whiteboard as well. Welcome. So today, we're going to look at differentiating trig functions. Differentiating functions. Differentiating functions. Okay, but we're going to look at a range of functions. So we will look at exponentials, logarithms, trig functions, so trigonometric functions. So these are the three main types of functions we will look at. Once we've had a go at this, then we will try to do some more interesting things. So trig functions, logs, and exponentials. I think that's all we'll kind of do. The exponentials will kind of be a very small part, but it's just still worth looking at. I think there are some key things that we can learn in here. Fantastic. Hi all. Okay, this is great. So first off, let's recover and recall what we know. We have polynomials. Okay, and basic functions. So polynomials and basic functions. So why I'm not calling everything polynomials is because some of them are not. So we've got things like this. So x squared plus x to the power of a half plus x to the 3/4. If I call the function if I called this a function, it's easy to differentiate. It's not a polynomial, but it kind of looks like a polynomial. We can differentiate that. We can also differentiate it bracketed functions. And you're like, what are bracketed functions, Mr. Dharma? And I will say things that look like this. F of x are x squared plus 7 to the power of 3. I could expand it, but by using the bracket rule, I will get a nice different derivative. So multiply by the power, take 1 off the power, multiply by 0 to the inside, which is 2x in this situation. Okay? So all in all, these functions we understand. And this bracket rule is going to be really important to us, okay? So I'm going to spend a bit more time, emphasizing how important this is. Okay, fantastic. So if you guys are comfortable up to there, please let me know by saying, yep, Mr. Dharma, that makes perfect sense. Okay. I'm going to start with exponentials. Okay. And I just want to add, the thing we learnt in bracketed functions is this part here. Ooh, that is not the right. That was wild and unnecessary. Alright, so let me just quickly check. And also just... Sorry guys, my computer's being a little funny. Oh, here we go. Okay, so we learned to differentiate then we did this multiply by the derivative of the, I'm going to say inside. This was sort of our takeaway. And whatever the differentiate part looks like is going to be the thing that changes. Right? The differentiate part is going to change, but the multiply by the derivative of the inside is going to be something that stays with us all the way through how we differentiate. That is the bracket rule that we're going to borrow. That is the quote-unquote chain rule thing that we're going to borrow. Okay, that's going to be on the bottom of everything that we do. Okay, polynomials, how do you differentiate? You multiply by the power and you take one off the power. Then you multiply by the derivative of the inside. Now let's see what the exponential situation is. It's going to be quite cool. So let's have a look. If f of x equals e to the x, then f dash of x is equal to e to the x. An exponential function, the basic exponential function, the derivative is itself. And that is kind of wild. Its gradient function is itself. So if you have an exponential function, if you want to differentiate it, you write itself. Pretty simple. Pretty nice. And that's what's so special about the exponential function. Remember, you have a special case. So does not necessarily mean this stays true. No, this is not true. However, the exponential e equals a number that is 2.718, and that's a special case. That's a special case where the derivative or the gradient function is the same as the original function, and that's kind of wild. So normally it doesn't work, but if it's e to the power of something, it does work, and that's why e is a really cool operator. And you're like, okay, cool, that's a fantastic thing, Mr. Dharma. So what about this then? Example. Find f dash of x if f of x is equal to the 2x. Okay? So let's do that. Well, f of x equal to e to the 2x. And so f dash of x is equal to e to the 2 of x. Am I done? No. Okay, so the basic function, how to differentiate, you don't do anything. But you've always got to append multiply by the derivative of the inside. And in this case, the inside is the power. So for this one, I've got to multiply by the derivative of 2x, which is equal to 2. And so in fact, the derivative of e to the 2x is 2e to the 2x. Does that make sense? Okay, let's try another example. Okay, I'm just going to quickly just change something, guys. Nothing's wrong, I just don't like how I've written it. Here we go. Find f dash of x f of x is equal to the x squared. Okay? So similarly, f of x is kind of nice, and f dash of x, once again, the basic derivative of e to the x of an exponential stays the same. But I multiply by the derivative of the power, in which case it is 2x. And so the final derivative can be rewritten nicely, but you don't need to. Okay, and so that's what I want you to take away. This whole green business over here of multiply by the derivative of the inside is the thing that we're going to carry, regardless of how nuts it looks. I'm going to do one more example, and then we're going to move on. Find f dash of x if f of x equals e to the x squared plus 7x. Okay, give it a go. I'm going to just wait and see what you guys can come up with. I'm going to give you about a minute. Okay, give this a good think, because it's not really super hard, but it takes a bit of thinking. Fantastic, Eddie. I think that's quite correct. So let's have a see and see how we go. First off, the derivative of an exponential is itself. So I will write the function. And then we do the green part, which is multiply by the derivative of the inside, in which case it's the power. So the derivative of this is I multiply by 3, take 1 off the power, then I multiply by the derivative of the inside again, in which case it is 2x. Boom. This is how I differentiate e to the power of something gnarly looking. You could try to simplify. I wouldn't. I think it looks just as good right now. Can you please just comment in the chat? Tell me if you've got that. Okay, that'd be really awesome. And if not, let's just process that again. The derivative, I write the function. Then I've got to multiply by the derivative of the inside, which is the power in this case. And that is, it's like one of those polynomials. Multiply by the power, take 1 off the power, then multiply by the derivative of the inside. And now the new inside is x squared plus 7, and the derivative of that is 2x. Fortunately for us, we know how to do that. Does that make sense, team? Can I simplify it, please, Jason? I don't want to, but I could write this. I don't think this necessarily looks any better, Jason. Why do I do it twice? Lucy, I'm not doing it twice. Because remember, if this was my function, the derivative of this function already has multiply by the power, take one off the power, multiply by the derivative of the inside. And so for this part, the derivative of the inside is this thing here. Right? We've got to fully differentiate everything. The inside derivative is this whole thing here. But, you know, it kind of looks like we are simplifying or doing the multiply by the derivative of the inside twice, but we're not, because each time we have a function inside a function, we will need to do that. And Jason, no, we will not need to simplify in the exam, because depending on the kind of context, if it's an achieved merit question, it probably doesn't want us to simplify. If it's an excellence question, you might need to use this information for something. But I think this is quite hard to get your head around at the start, but I think it becomes natural after a little while. Okay, are we okay with that? Can I move on to the next set of functions? Okay, I was just trying to figure out how I wrote this. Okay. Can you give us one more practice for the boys? In fact, yes, I will. Okay. Mustafa, this is for you. E to the power of 3x squared plus 7x to the power of 4. Okay? Give that one a go. Okay? I'll come back to it in about 5 minutes. Okay? E to the power of 3x squared plus 7x to the power of 4. Okay. So I'm going to come back to that question. So hopefully you've written it down in that time. If not, just holler and I'll go back there. But logarithms. So the standard log function, if f of x is equal to the natural log of x, then, okay, and we're going to just work with the natural log. If this is equal to the natural log of x, then f dash of x is equal to 1 over x. Once again, this is not true. Remember, if this is f of x is equal to log base 2 of x, then this doesn't hold, right? That was meant to be in red. Okay, we don't copy that. We're looking at the natural log. Remember, ln of x equals log base e of x. And that's why the special function e is really key, right? E is a special case. It does something very particular at a very particular time. Okay, so I'll come back to that answer for Mustafa in a little bit, but let's carry on. Let's see some examples. What do you think? Find f dash of x if f of x equals ln of 2 of x of 2x. Okay, so similar to before, f of x is equal to ln of something, and so f dash of x, according to the ln rule is just 1 over the inside. Okay. However, because of the green thing before, where we said multiply by the derivative of the inside, I'm going to multiply by the derivative of the inside, which is 2x. The derivative of 2x is 2. And so, simplified 2x over 2, this simplifies to 1 over x. Okay? It's kind of interesting. I'm going to actually just put another one next so we don't make things awkward. Okay? Suppose f of x was equal to ln 2x plus 1. Right? Nothing too different there. It's just ln stands for logarithm with a natural base. So ln, log natural. Okay? Natural log is the log that has this special property of when the derivative is itself. Okay? E has that special property. When we get more into differentiation, I will explain that. But for now, ln stands for natural log, and natural means the standard, the one that's really nice. Okay, so coming back to this, I differentiate. So I write 1 over the inside, and then I multiply by the derivative of the inside, which is 2. So this time it's 2 over this. Okay, and so that is our derivative. And in fact, you will find that that's really, really nice. Nothing more aside from if you differentiate in ln, you put whatever's on the inside on the bottom, and then you multiply by the derivative of the inside. Shall we try something slightly more complicated? I will take that as a yes. Find f dash of x if f of x is equal to ln of x squared plus 7. Alright, similarly, let's give this a go. I'll leave this for you to do for a second, and then I will give it a go. And in fact, I'm going to put another one down here as well. If f of x okay, let's see if we can make these work. Right, those two questions are for us to do. Okay, I'm going to start with this one. F of x equal to ln x squared plus 7, and so the derivative is inside, and I multiply by the derivative of the inside, which is 2x. So that simplifies to 2x over and so there's some cool notation that we could use that I probably will use later, but I'll do one more and then I'll use that notation. Okay, it's quite cool. It's not necessarily super exciting, but sometimes it's quite cool. So let's have a look. Can you just comment if you've got that for me? That'd be awesome. Okay, and then this one here, once again, ln brackets x squared plus 7 to the power of 3 close brackets. Now, 1 over the inside, which is this, multiplied by the derivative of the inside, which is once again multiply the power, take 1 off the power, multiply by the derivative of the inside, which is 2x again. So, simplified is 3, or let me just, 3 times 2x is 6x, yes. 6x times x squared plus 7 squared all over x squared plus 7 cubed. Right? Some of you might want to simplify this to 6x over x squared plus 7. And I'm going to leave that to you to decide. This is correct because the two x squared plus 7's cancel. And I want to show you something pretty awesome. Okay? And now, why I want to show you is, I want to show you why logs can be really useful to us. So, let's look at our function again. Right? F of x is equal to the power of 3. Yes? Now, because of log rules, I can bring the power to the front. Okay? And so now that 3 is just a constant at the front. So the derivative is equal to 3 times the derivative of this. And what's the derivative of this? It's 1 over the inside times the derivative of this, which is 2x. And if you kind of look, that is 6x over x squared plus 7. And so I've done this question in two ways. One using log rules and one not using log rules. And I got the same answer. And so in this itself, you can see that there's some really cool, nifty things happening, and you've got to be careful and try to be a bit more elegant, let's say. And so those of you looking at Skull, this is the kind of stuff that, makes a little bit more sense if you do kind of prettier. But I like this. I really like this. And I think it's really important that we understand that we can do things in many different ways. I am going to actually skip my section on like cool notations of this until our next session, maybe. And I want to just do the last little bit, okay? Just let me know that you are okay with this, please, and thank you. The first one we've got is if f of x is equal to sine x, the derivative is cosine of x. And that's cool. That's very cool. Now, we've spent a lot of time with trigonometry, and the relationship between their derivatives is even insane. So the derivative of the sine function, the thing that goes like this, is the cosine function, the thing that goes like this. I've drawn it horrendously, but that's no matter. You draw it, and it's kind of crazy. It's kind of the most insane, wonderful thing that we can get from maths. And if you come to my scholarship session, I can show you exactly why soon. Okay, if that is that, I'm going to write a couple more. If f of x is equal to cosine of x, then f dash of x is equal to negative sine of x. So sine goes to cosine, cosine goes to negative sine, and then negative sine goes to negative cosine, and negative cosine goes back to sine. It's kind of a nice pattern. I won't write those for you though. These two are kind of the most important. So similarly, let's try. Oh, I really tried, guys. Yeah. So this example, find dash of x if f of x is equal to sine of 2x. Okay, and actually I'm going to put like a whole bunch of these up for you already. Find f dash of x if f of x is equal to sine of x squared plus 7, and then find f dash of x if f of x is equal to sine of x squared plus 7 to the power of 3. Okay, my whole thing is I'm not going to try and make maths awkward and unnecessary for you. So, that's why I'm using the same insides as before, because that's not the thing I want to focus on. The insides will stay the insides regardless. What I'm focusing on is, do you understand? Do you understand the nuance of how the functions change? And if you do, I'm happy. If you don't, that's what we're going to focus on. All right. Okay, so let's just see how they go. Let's just yell these answers out, kind of. Okay. F of x, it's a sine function, and so the derivative of sine is cosine. Then I multiply by the derivative of the inside, which is 2, so I rewrite that as 2 cosine 2x. And these then become very, 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 very simple to do. So, sorry, wrong colored pen. Okay, f of x is equal to sine of x squared plus 7. And so then f dash cosine, the function changes. And then I multiply by the derivative of the inside, which is 2x. Can be 2x cosine x squared plus 7x. Okay, and then the last one I am going to do quite quickly because y'all are like, Mr. Dharma, we'll get. And I know none of you have seen the comment, but I feel as though you guys can see how this is very difficult after you know the situation. You change the function. This function for us is cosine, and then you multiply by the derivative, which now we are almost fluent in writing. And this I wouldn't rewrite in any other way because it looks kind of linear. X squared plus 7x cos x squared plus 7 cubed. Right? Boom, done. This is us. Right? These three functions that I've asked you to differentiate are really, really nice in this kind of way. All right, I'm going to just wait a minute or so just to see if you guys have comments or questions in the comments, and then I'm going to see if I can respond to that, and then I'm going to show you what I want us to look at really quickly after this. And Mustafa, if you'd really like me to go over that question I put up, can you also type that in, and I will. Otherwise, I will leave that for you guys to do in your own time. Maybe afterwards when you come back and pause the video, you can come back and That'd be awesome. Some of you might be wondering why I haven't done tan. And why haven't I done tan? Tan is really interesting. I will do tan tomorrow, but not tomorrow, Thursday. But to do tan, I need you to be comfortable with what sine and cosine do. If you can promise me that, then I will do tan on Thursday. Otherwise, you guys miss out on tan. Okay? Okay, perfect. Now, sweet. Awesome stuff there, Mustafa. And no one's really asked me any questions. So what I'm going to show you now is the table of derivatives. So the lucky thing that you get given is a definition list, a list of derivatives that you just should know. Okay, so you don't need to go through this kind of notes for everything. And here it is. I'm just going to try and pull that up and see if I can. If not, it's going to be awkward. Give me 1 second, team. I'll just quickly pull up this document that I think is super important. Boom. All right. I'm just trying to make this a little bit bigger, and let's hopefully not lose resolution. Ooh, there we go. Okay. So, we have just covered ln. This is from your formula sheet, by the way. Exponential. I do not like this notation. This is bad notation. Okay, because it's not just the coefficient, it's the derivative. Okay, so I don't like the notation NCEA uses, but that's okay. So I'd want you to remember that it's the derivative. I've shown you sine and cos goes to negative sine. You can just use these, tan, cosec, sec, and cot. It's just know that this, and you can just use them. And this comes from your table of derivatives, and in the future, like if ever you decide to do maths afterwards, you get pages and pages of tables of derivatives, because sometimes it's harder to find the derivative by first principles than to just use it. And when I say first principles, yes, I mean last Wednesday's lesson. How these are got are from how last week's lesson went. So if you use first principles and some trig identities and some crazy other stuff, you can make this whole table. And I think that's pretty gnarly. I think that's pretty awesome. I also want you to just look and see that tan is here, but I'm going to show you tan in a really cool way on Thursday, because this is nice, but I want to show you why this is, and I won't use first principles. Okay, I'm going to just leave this here. I'm going to challenge you to try a few questions like this, see how you go, and see what happens when you nest some of these functions together, because that's something very interesting. And so what I'm going to do is I'm going to give you an example of a question that's really interesting, something that I think we should spend a lot more time doing. Okay, find f dash of x if, oh, that's wrong, if f of x is equal to sine, oh, my whiteboard just crashed. Well, team, that's a bit awkward. Let me see if I can bring it back up. That was very awkward. And oh, fantastic. Yep, just give me a second to scroll. Just give me a second, sorry team. Here we go. Okay. If f of x is, are you ready for this? Okay, so have a look at this. This has got a sine inside, oh, sorry, it's got a polynomial inside an exponential inside a sine. This is nuts, but you can do it. Okay, give it a go and see if you can make sense of it. Okay, if not, follow along with me. Questions like this are good to know because they might pop up in Merit Excellence questions. I think it's quite nice to do it this way. So, unfortunately, what I didn't realize is that you still can't see my screen. This is really awkward. I'm so sorry, guys. So anyway, whilst I try to get this back, if you guys could just maybe in the chat just converse and try to figure out some interesting, I will endeavor to get this working again. Yeah, I see you got the blue screen. Unfortunately, I'm trying to fix it, and oh, perfect. I think I've got it again, guys. Yep. All right. Sorry, guys. This is technical difficulties at their worst, but guess what? We will survive. My year 12s the other day, I lost the whole thing, so it was a bit awkward. Yeah, sorry, guys. Yeah, it's back now, I think. So let me know if it's not back. So I'm going to go through this question now. Yeah, I didn't look at my monitor. Okay, so first off, I want to differentiate. So the first and outmost function is sine. So sine differentiates to cosine, but the rest stays the same. Then I multiply by the derivative of the inside. The derivative of the inside is the derivative of e to the power. So e as a function stays the same. Then I multiply by the derivative of the inside, which is 2x. Ain't that crazy? Hello, Lucy and Charlotte. Thanks. Thanks for keeping everyone entertained. But look at how nuts this could have been, but it's actually not that bad. Right? I've differentiated the sine to cosine, then looked at the inside. What is the derivative of an exponential? Still an exponential. And then I've differentiated the inside. What's the derivative of a polynomial? Once again, another polynomial. Boom, boom, boom. It's quite elegant. I'm going to put one more up now that you can actually see it. I'm sorry. Okay, give this one a go. Okay, and I'll give you a couple of minutes and then we'll go through the answer and then I'll call it a day, unless you have questions. So if you have questions, just type them in now and we will have a look at them. This work is these questions are much harder than anything in your workbooks or anything your teacher will give you, but I think it's still very fundamental that you understand this stuff. And Mustafa, thank you for understanding about my technical difficulties. And Skillingham, welcome. I don't really know who you are, but this is great. Thanks for letting us know. Yes, exactly. Until your function becomes linear, until your function doesn't have something inside it, right? And that's pretty much how you go. So I'm gonna just give this a go and see what happens, okay? So first, cosine goes to negative sine, then everything the same. Then e stays the same. Then I multiply by the derivative of the inside. The derivative of the inside here, this situation here, so that's multiply by the power, take 1 off the power. Then I once again multiply by the derivative of the inside. 2. I am now done. Ain't that a crazy situation? You could try to simplify this, but to me it doesn't need to. It's more of the understanding of how this works. And so the other day when I was calling the bracket rule something, we now call it the chain rule. And we can call it a chain rule because you can sort of see how it sets off a chain reaction of these multiply by the derivative of the inside, multiply by the derivative of the inside, multiply by the derivative of the inside, every single time until it terminates. And I think that's powerful. And that's why it's called a chain, because it sets off a chain reaction. Oh, hi, Max. Yeah, so it sets off a chain reaction, and that's sort of where you see it. And later on, when we get to better notation, um, or Leibniz notation, I'm going to show you a better way to look at this as well, and that will be really cool. But that's not going to be for a little while yet. But I want you to understand these functions, how they differentiate, and essentially be very, very comfortable with this table, knowing the caveats of what this section here is. You know that I don't like the notation, it's bad notation. But I expect you to be able to use all of these quite comfortably, and we will have a chat about some interesting stuff next time on Thursday. On Thursday, we'll be doing some differentiation rules. Okay. I'm hoping you guys enjoyed that. I'm going to put this answer back here just for those of you who want. It looks way harder than it actually is. Jason, you're absolutely right. It's the fact that you've got to take it step by step. Go small steps, and small steps, and you'll make it work. Because if you compartmentalize and just look at the small thing, then it's fine. If you try to do all of it at once, it's really, really tricky. And so, yeah, thank you for picking up on that, Jason. It looks harder than it is. Nice. All right. Feel free to send me an email if you get stuck. Talk to your teachers, and I will see you on Thursday, unless there's any other questions. Mustafa, thank you. I'm so glad you enjoyed that. Right? No. Really enjoyed this, and hopefully you guys are taking time to relax and look after yourselves. Please don't stress. I'm not doing these to stress you out. I'm just doing this to provide you an opportunity to continue learning. Remember, it is an unprecedented time, and so look after each other and be kind to one another. All right. Thank you, team. Bye for now.